Hello everybody, welcome. This is paper 1 from May 2022, and this is time zone 1. So I think this is actually quite a challenging paper. Last question, 13 mark question here. A ball is dropped from a height of 1.8 meters and bounces on the ground. The maximum height reached by the ball after each bounce is 85% of the previous maximum height. Show that the maximum height reached by the ball after it has bounced for the 6th time is 68 centimeters to the nearest centimeter. Okay, so we have the ball, it's being dropped from an initial height of 1.8 meters, and then each time afterwards it only rises to 0.85 or 85% of its previous height. So if we were to write an equation for this, and let's say this is the bounces and this is the height, what could we do? So 0 bounces, it's at 1.8. After the first bounce, it goes up to 1.8 times 0.85. And I'm actually just going to work that out. 1.8 times 0.85 is 1.53. And then after the second bounce, again, we would multiply by 0.85. So in this case, we actually have a geometric sequence. When we have some starting value and we multiply by some constant term as we go through it, and we have a geometric sequence. So in this case, there's A. Show that the maximum height reached by the ball after it is bounced for the 6th time is 68 centimeters. Our geometric sequence formula is given by UN is equal to U1 times R n minus 1. U1 is the value of the first term, and R is the common ratio, what we multiply by to go from one term to the next. So conceptually, we can think of this, if we want to find the maximum height reached at its 6th bounce, we can ask ourselves, okay, well, how many times do we need to multiply by R, this 0.45, in order to get there? So here is 1, 2, and the distance should be, I'll just, 3rd bounce, 6th bounce, 5 times. So in this case, if we want to find the height from the 5th bounce, we know that U1 is going to be 1.53. So this one's a little tricky because our first bounce is right here. It's not actually equal to 1.8. This would be in some sense the drop height, so it's not yet bounced. The first bounce of U1 doesn't happen until we multiply 1.8 times 0.85. So this is our first bounce times, and then the common ratio of 0.85, and then times n. In this case, n is equal to 5, so let's just substitute 5 minus 1. 1.53 times 0.85 times 5 to the 1. So let's put this into the calculator. 1.53 times 0.85 raised to the power of 5 minus 1. 5 minus 1. Essentially 5 minus 1 is 4. It's not a bad idea to write that out just so you don't get mixed up for brackets or order operations or anything like that. Okay, so, or sorry, it's a 6th bounce, isn't it? So n minus 1 would be, I'm actually going to write it out this time, 6 minus 1. And there we have 0.678869. So going back to the document, we have 0.6789, or rounding to just to the nearest centimeter. Remember, this is in meters actually. This is in meters. So multiplying by 100, we have 67.89 centimeters, or 68 centimeters. Okay. Alright, so I think the trick in this one, or maybe the challenge, is this is the value of the first term. And the first term doesn't correspond to the drop height itself. It corresponds to the height reached after the first bounce. So drop height times that 0.85 or 85% to which it rises to. So that's our U1. And then R, we still know is our common ratio. And then n minus 1. N minus 1 is the n minus 1 is the number of times we're multiplying by to get 2, and since it's the sixth term, n is just going to be 6. I'm sorry, here I had written it as 5. So sixth term, 6 minus 1. Okay, part B. Find the number of times after the first bounce that the maximum height reached is greater than 10. So we've kind of done the hard work, and we've got an equation which is 1.53 times 0.85 n minus 1. Find the number of times after the first bounce that the maximum height reached is greater than 10 centimeters. So if we look at this, every single bounce, it goes less and less and less and less and less and less. We want to find the number of times that this bounces such that the maximum height reached is greater than 10. So we know it's going to get less and less and less, but what is the number of bounces that we can possibly have where the bounce height is still just greater than 10? So maybe it just makes it over, and then the subsequent bounce would be, in this case, reduce that a little, just less than 10, so it doesn't quite measure up, not quite there. So we want to find what bounce is that, what number. Alright, find the number of times after the first bounce that the maximum height reached is greater than 10. In this case, this value, this is UN, which is just the value of the nth term. In this case, we want the value of the nth term to be equal to 10. So we have 10 is equal to 1.53 times 0.85 n minus 1. And in this case, we're looking for that value of n that's going to solve this. So we can just go ahead and n solve. So let's go ahead and do that. So menu, algebra, solve, 10 equals 1.53 times 0.85. Then we want to raise this to the power of n minus 1, and then we'll put a value of n. Okay, and for some reason this is, I see. Okay, so sometimes this is just me being careless, to be honest. You can have a look and see what the problem is. This negative 10 is impossible. This 1.53 is measured in meters, where this was given to us in 10 centimeters. So negative value, obviously not really coherent. So we can either convert this into meters or convert this into centimeters. I think it's going to be easier to convert this 1.53 meters into centimeters, and 1.53 times 100 is just going to give us 153. And in this case, we have 17.7848 ounces. So going back to the document, in this case, n is equal to 17.78 bounces. So the number of times after the first bounce that the maximum height reached is greater than 10. At 17 bounces, we're still greater than 10. At 18 bounces, we would be less than 10 centimeters because each bounce we're decreasing. We don't really have 17.78 bounces. We only have whole number for our bounces. So in this case, the number of times after the first bounce that the maximum height reached is greater than 10. In this case, n would be equal to 17. After the 18th bounce, we would then be smaller. Or after the 17th, once we reach the 18th, we'd be smaller. Okay, let's go to part C, asking us to find the total vertical distance traveled by the ball from the point at which it's dropped until the fourth bounce. So what makes this one a little challenging, and I suppose we could suspect that it might be challenging given that it's the final question on a paper 1 and it's also a 3-mark question here. The total vertical distance is going to be not just this initial drop height, but what makes this extra challenging is that we have the ball traveling upwards, but also the ball traveling, of course, downwards on its way back. So the total distance that this ball travels would be not only its, on its way up, but the total vertical distance is going up and then going down again. So it makes it a little more challenging and some extra kind of pieces involved. So we've got this geometric sequence here, and we've got a formula for it right here. So let's go ahead, and if we know, let's say, the value of the first term, and we know the value of r, we should be able to find the sum of the terms of a geometric sequence using our geometric sequence formula. So let's go into the formula booklet. Here it is already, I suppose. I'm just going to erase this and then mark it up once again, I suppose. Here we go. So Sn is the sum of n terms, so the number of terms of a geometric sequence. U1 is the value of the first term, r, our common ratio, and then n is, of course, the number of terms that we want to find the value of. So let's go back to the document and write this out. So Sn is equal to U1, value of the first term, times Rn minus 1 over r minus 1. We saw that there were actually two formulas. I'm just going to write out the other one right here. R to the n over 1 minus r. They're the exact same thing, except these values of 1 and r are switched around. And what that does is when r is less than 1, so for example in our case we have 0.85. 0.85 minus 1 is just going to put a negative value. And so these formulas are actually equivalent. They mean the same thing, and you can use either one as long as you're mindful of your brackets and so, and your negatives. Either will be okay. So it's just to avoid negatives if you wanted to work this out maybe by hand, I suppose, or in smaller parts. So let's go ahead and work this out, reading the question really carefully this time. Find the total vertical distance the ball is dropped until the fourth bounce. So in this case, this is U1, this is U2, and this is U3. So this is just 1.8 right here. This is the value of U1, the value of U2, and this is the value of U3. We don't want to include the fourth bounce. It's until the fourth bounce, which is dropped until the fourth bounce. Maybe some kind of ambiguity here, but the idea is we don't want n is equal to 4. We don't want to include this last type. We just want n is equal to 3. So let's go ahead and find the sum of the first 3 bounces. So U1, 1.53, common ratio of 0.85. In this case, n is equal to 3, minus 1 over 0.85 minus 1. Let's go ahead and put that into the calculator. So 1.53 times, I'm going to open up some brackets and then get a fraction here. 0.85 to the power of 3 minus 1. Then we have 0.85 minus 1. Okay. And there we go. Let's go back to the document. The value is 3.9359. Remember, this is all in meters so far. And so to 3 sig figs, I'm going to write this out as 3.94. Okay, 3.94 meters. And just looking back here, just to get a conceptual idea, this initial drop height was 1.8. and then the sum of the heights of each of these is going to be, actually, was it 3.94? But really, that's just the vertical height on the way up. So blue is equal to 3.94, and then on the way down it's also another 3.94. So a lot of pieces to potentially, you know, maybe kind of trip you up in some kind of way. And to be honest, I mean, it did for me the first time I read this. 1.8, sure, we have to only have one bounce here. It's the way up and the way down. Multiply by 2, sure, but this part until the fourth bounce. So we don't actually include this value of U4 in this instance. It's only up until this value, so we only want to take the first 3 bounces. So, putting it all together, total value, that initial height of 1.8, that's the initial drop height, plus 2 times the sum of the next 3 bounces. I'm actually going to write out all of the digits just because we don't really want to put 3 sig figs until the question is over at the end. So 3.9359. And let's work that out. I'm going to put that on my calculator that I have beside me. 3.9359 multiply by 2 and then add 1.8. And this gives us 9.67 meters. And it doesn't ask for centimeters or meters, so we can just keep it like that. Okay, alright everyone. Not a bad exam. There's some questions that definitely required some more interpretation. The earthquake question, for example, this final question, where a close reading is potentially super important. I suppose all along, though, make sure to show process marks, maximize, and of course you'll be rewarded in that sense. Alright, everybody. I hope that was helpful, and as always, best of luck. Take care.